In this section, we're going to begin exploring the world of algebra, where numbers and letters go hand in hand in equation form. This may be different than the math you've done to this point, but don't worry, it's not that different. In fact, many of the same ideas apply. We're still going to be multiplying and adding and all that fun stuff.
The first thing we want to do here is open our cognitive passageways for some words of wisdom that'll help us through the next couple sections.
In algebra, it's very common to see numbers and letters together, kind of like peanut butter and jelly. When we see letters like x or n in an equation, they're called variables. When we see regular old plain Jane numbers, they're called constants. So, if we see something like x plus 2 equals 6, x is a variable, and 2 and 6 are constants. And when we see a number and a letter directly next to each other, like 14x, we call the whole unit a term, and we call the number our coefficient. Note that 14x also means 14 times x.
Now in algebra, there are certain terms that we can combine and others that we can't combine.
It's kind of like we can combine popcorn and get more popcorn. But if we tried to combine popcorn and sneakers, we'd just get popcorn in our sneakers.
So let's say we had the terms 4x and 8x and wanted to add them or subtract them. Here's how it works.
If we've got 4x and 8x, we can add them together to get 12x. We can do this because both our 4 and our 8 have an x attached to them. This is called adding like terms. Now, we couldn't add a plain old 4 to an 8x and then get 12x. These aren't like terms. We just get 4 plus 8x.
Likewise, we can subtract the like terms 5x minus 2x and get 3x. But we can't subtract 4 from 10x. We just have 10x minus 4. See what I mean with these x's? When we add or subtract terms, our x's have to match up.
Okay, so we've got variables, which are the letters, constants, which are the plain old numbers, terms, which are a number and letter together, and coefficients, which are the numbers in front of the letters.
When we add or subtract with x's, we can only combine like terms. And when we see something like 7x, this means 7 times x.
Now, let's go ahead and look at how this stuff turns up in equations.
Section B, equations.
An equation is a mathematical expression with numbers and letters mixed in. Its main feature is a lovely equals sign, as well as two sides that are equal to each other in value. X is one of the more common letters used in equations, and it's going to be our variable of choice. As we work with equations, our main goal will be to solve for the numerical value of x.
So if we see something like 3x plus 5 equals 20, we've got to figure out a value for x that will make the left side of our equation equal the right side.
A good way to imagine equations is to think about them like a scale. What would happen if you were carrying 75 pounds of portobello mushrooms on your right shoulder, but only 5 pounds of portobello mushrooms on your left shoulder? At best, you'd lean like the Tower of Pisa, but it's more likely you'd just fall over.
So, in order to keep you upright, we'd have to figure out how many more portobello mushrooms you need on your left shoulder to keep you balanced. That number of mushrooms would be the x of our equation, the mystery we need to solve, the golden x.
Ladies and gentlemen, I give you X.
So, when we see an equals sign, it means that both sides of the equation need to weigh the same. This means that as we go through the process of solving the equation, whenever we put something on one side, we've got to put it on the other side too. Otherwise, we'll tip the scale. And you don't want to be a scale tipper.
Section C, the golden x.
All right, with all that intro stuff behind us, finding x will be a piece of cake. Take a look at these equation forms in letters, then we'll stick some numbers in.
The first equation looks like this. It takes the form a times x equals b. In this equation, x is our variable, and a and b are constants. Remember, constants are just plain old numbers, and we don't need to solve for them. So, let's take an equation where the value of a is 4 and the value of b is 12. That means we've got the equation 4x equals 12. Remember, we're trying to figure out the value of x. Therefore, what we've got to do is figure out how to get x on a side all by its lonesome self. So, What can we do to get rid of the 4 that is partnered up with the x?
Going once, going twice, you divide it.
Right, you just got to divide it. So we've got 4x equals 12, and we're solving for x. We simply divide each side by 4. When we do this, our left side is 4 divided by 4, which equals 1, so they cancel out, and we're left with an x. On the right side, 12 divided by 4 equals 3. So our answer is that x equals 3. And as an added bonus, we can always check our work by plugging the answer back into our original equation. In this case, plugging 3 in for x in the original equation, we get 4 times 3 equals 12. In fact, 4 times 3 does equal 12, so we know we got the right value for x.
Now, in case you're wondering why we divided by 4 to solve for x, it's because the term 4x means that 4 and x are multiplied together. So in order to get the x alone, we've got to do the opposite of multiplication, which is division. Got it? Let's try another one and you'll see what I mean.
What if we had 7x equals 63? Well, we know that 7x means 7 times x, so in order to get the x alone, we've got to divide both sides by 7. When we do this, our 7's on the left cancel out, and we're left with x. And when we divide our 7 into 63 on the right, we get 9. So we've got x equals 9. Now we can use the dynamic check to figure out if we've done it right. We just go back to our original equation and plug in 9 for x. We end up with 7 times 9 equals 63. Sure enough, 63 equals 63, so we're right.
See, it's a lot like a puzzle where we're searching for the missing piece that will balance our work. Let's look at another equation form.
Okay, the next equation is the form of ax plus b equals c, where a, b, and c are all constants. This time we've got another constant, but our mission is still the same. We've got to solve for x, and we can't tip the scale. So let's put some numbers into this and give it a shot. What if we have 5x plus 3 equals 18? How do we get x on a side by itself so that we can solve for it?
In this case, we want to move the 3 first. Because 3 is added on the left, we need to subtract it. And remember, the key is that we've got to subtract it from both sides to keep the scale balanced. So we bring down the 5x, then subtract 3 from 3, and 3 from 18, giving us 5x plus 0 equals 15. To simplify, we get rid of this 0 since it's just hogging space, and we've got 5x equals 15.
Now, just like last time, we divide. Here we divide both sides by 5. Our 5's on the left cancel out, and on the right side, 5 goes into 15 3 times. So we've got x equals 3.
And now for the check. We just plug our x value back into the equation, and we've got 5 times 3 plus 3 equals 18. And in fact, 5 times 3 equals 15 plus 3 equals 18. Our solution checks.
Another similar example is 4x plus 4 equals 20. In this case, we subtract 4 from both sides first, giving us 4x plus 0 equals 16, or more simply, 4x equals 16. The next step is to divide each side by 4, which gives us our final answer of x equals 4. To check, plug in 4, and we've got 4 times 4 plus 4 equals 20, which gives us 4 times 4 equals 16 plus 4 equals 20. Our solution checks.
So you see, Mr. President, it equals 20.
Oh, so it does. 20, our solution checks.
There you forgot the smiley face in that last 0.
Oh, my bad.
Okay, the next equation form looks like this. ax plus b equals cx. Yep, get your pencil out and write home. That's 2 terms with x's.
So it's double the fun. This time we've got 2 terms with x's, and what you gotta do is get these 2 terms together. Let's get some numbers to work with here.
Say we've got the equation 3x minus 4 equals 2x. The first thing we do is combine our x's. Here, we can do this by subtracting 3x from each side. This might look a little weird because we're subtracting a term with an x in it, but this is the way we get the x terms together so we can solve for a single x. When we subtract 3x from each side, we get negative 4 equals negative 1x, which we write simply as negative x because it means the same thing.
Now we're not quite done because we want our x to be positive. We can do this easily by multiplying each side by negative 1. The reason we do this is because 2 negatives multiplied together equal a positive, and because 1 times any number or letter simply equals that same number or letter. Basically, multiplying by -1 will allow us to change our signs. See how -1 times -4 equals +4, and -1 times -x equals +x. So we end up with +4 equals +x, or simply 4 equals x.
If we're right, our answer 4 should work in the original problem. Plugging it in, we get 3 times 4 minus 4 equals 2 times 4. When this is multiplied out, it gives us 12 minus 4 equals 8, or 8 equals 8. It's a check.
Okay, just one more equation form like this. This one's got a few more numbers. Check it out.
In letter form, we've got ax plus b equals cx plus d, where a, b, c, and d are all constants. For our example, let's make our equation 2x plus 2 equals 5x minus 4. Now, I know this time we've got more numbers, but our goal is still to get x alone. So, let's do it.
Our first step is to move the 2 over with the -4. Since we have a 2 added on the left, we've got to subtract the 2 from each side. Now we've got 2x equals 5x minus 6, and all our constants are together. But we've still got x's on both sides of the equation. So we subtract a 5x from both sides to get them together. We now have -3x equals -6. Next, we divide each side by -3. Our -3's cancel out, leaving us with x on the left. And -6 divided by -3 equals +2. So x equals 2.
To check, we plug 2 into the original equation for x and multiply it out. 2 times 2 plus 2 equals 5 times 2 minus 4. This becomes 4 plus 2 equals 10 minus 4, which becomes 6 equals 6. Woohoo! We're balanced.
Okay, let's switch gears a little bit. We're going to talk about an equation where we don't have to solve for any numbers. We just have to solve for a variable. In essence, we're just trying to get a particular letter on a side by itself.
No numbers?
No numbers. We're going to do an example using the formula for the perimeter of a rectangle. But before we solve the equation, let's go on a little tangent and talk about perimeters. Come on.
Say you're flossing your teeth and whatnot in a rectangle-shaped mirror. Well, the perimeter of the rectangle, in this case your mirror, refers to the outer edges, the sides that give the rectangle its shape. Notice these two sides, which are the longer sides. We call these the length of the mirror, and they are equal to each other. These two sides represent the width of the mirror, and they are equal to each other. So the perimeter of the rectangle formed by the mirror consists of 4 sides added together. 2 equal sides that are the length, and 2 equal sides that are the width.
So here's the formula for the perimeter of a rectangle. P for perimeter equals 2L for the length plus 2W for the width.
There may be times when you're asked to find actual number values for all of these variables, but the only thing we're going to do is solve for W, just the letter W. So our goal is to get the W on a side by itself, just like we've been doing.
To get W alone, the first thing we want to do is get rid of 2L on the right side because it doesn't have a W in it. So we subtract it from both sides and get P minus 2L equals 2W. Now we just divide both sides by 2, giving us P minus 2L all over 2 equals W. Notice that the 2 doesn't divide into the P minus 2L. That's because there's no 2 in front of the P, so it wouldn't divide in evenly. So this is as far as we need to go in this case because we got W on a side by itself.
Okay, we're really beefing up our equation resume now. There's just one more type of equation we're going to look at here. Check it out.
Okay, let's look closer at something we already know a little bit about. Let's see how absolute values work in equations.
Whenever we have an absolute value in equation form, we'll be solving 2 equations. If you remember, absolute values themselves are always positive. But before we actually determine the absolute value, the numbers involved could be either positive or negative. It's kind of like if you just say to someone,
"Okay, meet me at Spartacus's Munchery at 10 o'clock, and don't be late."
That sounds fine. Who are you again?
we don't know if they mean AM or PM, so we've got to consider both.
If we've got the absolute value of x equals positive 5, the x itself can be either positive 5 or negative 5. This is because the absolute value of both positive 5 and negative 5 is positive 5. This means we've got to consider both possibilities. So, if we're asked to give a value for x, we have to give two answers, positive 5 and negative 5.
Same thing here. The absolute value of x plus 3 equals 4 means we've got x plus 3 equals positive 4, and x plus 3 equals negative 4. We've got a positive version and a negative version.
Let's take a stab at the positive version first.
For the positive version of the absolute value, we take x plus 3 equals 4 and simply solve it like we've been doing. We subtract the 3 from both sides, and this gives us x equals 1. No problem, right?
Now for the negative. Remember, we've got x plus 3 equals negative 4. Just so you know, we could have chosen to make the left side of our equation negative instead, giving us negative x minus 3 equals positive 4. But we chose to make the 4 negative because it's easier to work with. When we solve the negative version of absolute value equations, we just have to make sure that one whole side is made negative. In our case, we made the 4 negative and got x plus 3 equals negative 4. Now, we simply subtract the 3 from both sides, which gives us an x value of negative 7.
So, our two answers for the absolute value of x plus 3 equals 4 are 1 and negative 7. Now, let's check these buggers.
For our positive version, we got an answer of 1, so we substitute 1 in for x and run this back through our original equation. We get the absolute value of 1 plus 3 equals 4, or the absolute value of 4 equals 4. Bingo! Our check checks out. Now for the negative version. We got x equals negative 7, so we substitute negative 7 for x and run it back through our original equation. Now we've got the absolute value of negative 7 plus 3 equals 4. When we do the math, we get the absolute value of negative 4 equals 4. Well, sure as fire breathes heat, the absolute value of negative 4 equals positive 4. So, bingo again, our second check checks. We got both correct solutions.
We're going to do one more example with absolute value equations. Say you've got the absolute value of 3x minus 5 equals 20. Remember, we've got to solve for two versions. You know the drill.
First, let's do the positive 3x minus 5 equals 20. Let's add a 5 to each side to get 3x equals 25. In order to get x all alone, we divide by 3, which gives us x equals 25 divided by 3. So we've got our answer for the positive version, 25 over 3. We leave our answer in fraction form because it doesn't divide evenly.
Now for the negative version. We're going to make that 20 negative because it's easier than making the whole left side negative. So we've got 3x minus 5 equals negative 20. First, we add a 5 to each side and we get 3x equals negative 15. Next, we divide by 3 and get an x value of negative 5.
So our two answers are 25 over 3 and negative 5. Now let's check them.
For the positive version, we plug in 25 over 3 for our x value and run it through the original equation. Now we've got the absolute value of 3 times 25 divided by 3 minus 5 equals 20. So we switch that first 3 into the fraction 3 over 1, so it's easier to multiply. Now notice how our 3's cancel each other out. So we're left with the absolute value of 25 over 1 minus 5 equals 20. Well, 25 over 1 just equals 25. So we've got the absolute value of 25 minus 5 equals 20. And 25 minus 5 does equal 20. So we've got the absolute value of 20 equals 20. Our check is good.
And now for the negative version. We take our x value of negative 5 and run it through the original equation to get the absolute value of 3 times negative 5 minus 5 equals 20. So we multiply our 3 times negative 5 to get negative 15. Now we've got the absolute value of negative 15 minus 5 equals 20. Negative 15 minus 5 equals negative 20, and the absolute value of negative 20 does equal positive 20. Our check checks.
To solve for x, we need to get it on one side of the equation by itself. In the process of doing this, we got to make sure that we don't tip the scale. Whatever we do to one side of our equation, we do to the other. If we've got an equation like 8x equals 16, we divide by 8 on both sides to get x alone. If there's a number that we subtract on one side, we've got to subtract it from the other. If we add to one side, we add to the other.
When we solve for x in absolute value equations like this one, we've got to solve both the positive and negative possibilities. When we solve the negative version, we have to make one whole side negative, then proceed with the same rules for regular equations.
Quiz 1.
Part 2, Graphing. Section A, the graph itself.
A graph is a grid that is divided into little square sections. It looks a lot like a waffle, but we don't usually put syrup on it.
We usually put two intersecting lines on a graph. One line is horizontal, like the form your body would take if you levitated out of bed. And the other is vertical, like your body would look if you were standing up and you stretched your arms way above your head. The horizontal line is called the x-axis, and the vertical line is called the y-axis. These axes are like two number lines that cross at their 0 point.
The coordinates are like our map. They tell us how far right or left we have to go on the x-axis and how far up or down on the y-axis. So, each point on a graph has a set of coordinates. We say that a point has an x-coordinate and a y-coordinate. The coordinates are written like this, in parentheses, with the x-coordinate first and then the y-coordinate.
So, if we had the coordinates of a given point that were 4 on the x-axis and 7 on the y-axis, we'd write them like this. Likewise, if we had 2 on the x-axis and 6 on the y-axis, we'd write them like this.
You might notice that these look like the intervals we were dealing with in the number line section. But don't worry, we can tell which one we're talking about by the context we're in. If we're talking number lines, then we're talking intervals. But if we're talking graphs, then we're talking coordinates. And if we're not talking at all, you may want to get your ears checked.
Hello?
So if we see the coordinates 2 and 6, our first step is to go to the center point of the graph. Notice Greta Guppy at the center point. We say that Greta is at the origin of the graph. The coordinates of the origin are 0, 0. So Greta, the graphing Guppy, always starts at the origin, then follows her coordinates. In this case, she swims over 2 places to the right on the x-axis. Next, Greta jumps up 6 places on the y-axis. Over and up. This is where Greta leaves her mark.
See how Greta made her mark in the top right section? This section is called quadrant 1. On a graph, the x and y axes intersect to create 4 sections. These sections are called quadrants.
Notice this squash. When it's in the top right corner of our graph, it's in quadrant 1. When our squash is directly to the left of that, it's in quadrant 2. When our yummy squash is directly below that, it's in quadrant 3. And when it's to the right of quadrant 3, everybody's favorite squash is in quadrant 4. Starting with the top right corner, the numbers of the quadrants follow in counterclockwise fashion. 1, 2, 3, 4.
Well, a graph is divided into 4 sections because there are 4 different combinations that coordinates can come in. So far we've only dealt with quadrant 1 because all our numbers have been positive.
If Greta Guppy is moving to the right on the x-axis or moving up on the y-axis, then Greta's got positive values.
But notice here, Greta Guppy is hanging out in the negative numbers to the left and bottom of our graph. This means when Greta's moving to the left or bottom, Greta's feeling a little down in the land of negative values.
So we can have points anywhere on the graph. The key to figuring out where our point should go is paying attention to the signs of our coordinates.
When our x-coordinate is positive and our y-coordinate is also positive, our point will be in the first quadrant. If we've got a negative x and a positive y-coordinate, then our point will be in quadrant 2. Points with a negative x and a negative y will be in quadrant 3. And if we've got a positive x and a negative y, our point is going to be in the 4th quadrant.
Okay, now that we know how the quadrant system works, let's try a couple examples to flaunt our skills. Say we want to plot the coordinates -3, +4.
Starting with a -3, Greta moves to the left 3 places on the x-axis because the numbers to the left of 0 are negative. Then Greta swims up 4 on the y because moving up puts her in the land of positive. So, she puts a point at -3, +4. Or, if we had the coordinates +6, -7, Greta goes 6 places to the right on the x and 7 places down on the y and makes her mark.
Now that we know all about quadrants, points, and coordinates, and we even know a little bit about guppies, it's time to take the next step.
Yep, it's time to connect the dots. But unlike the wild, haphazard days of our youth, we've got some rules to follow this time. So let's go over some of the stuff we'll need.
Section B, graphing linear equations.
A big part of connecting points on a graph involves linear equations. A linear equation is an equation whose solution points of x and y can all be connected to make a straight line on a graph.
All this means is we're going to have two letters in our equations now, x and y. First, we're going to figure out what numbers x and y stand for by solving the equation. Then, we're going to use our x and y values as coordinates to make points on our graph. And then, we'll use our crayons and connect the points to make a line. The cool thing here is that we're bringing together everything we've gone over so far.
Now, just like some of the other stuff we've done, we're going to look at it in letter form first, then we'll plug in some numbers and solve them. Let's try one.
All right, check out the form of our linear equation. ax plus by equals c. In this case, a, b, and c are all constants, and we're looking for the values of x and y. The only thing that's different than what we've already done is that we've got a y variable keeping the x company.
So, we might have something like this. 2x plus 3y equals 12. Because we're trying to create a line, we've got some room to fiddle with our x and y values.
So we can start by choosing a value for x or y and then solving for the other variable. As we solve for more points, we can put them on a chart to stay organized. Take a look.
Let's say we've got the equation 2x plus 3y equals 12. We can make a chart for our x and y values that looks like this. A good way to start is to pick a simple value for x, such as 0, but we can really pick any number we want. It's just that 0 is the most simple. After this, we plug it in as the value for x and solve for y. So when we put 0 in for x, we get 2 times 0 equals 0, which gives us 0 plus 3y equals 12, or 3y equals 12. Now all we gotta do is solve for y. We divide each side of the equation by 3, giving us 3y divided by 3, which just equals y, and 12 divided by 3, which equals 4. So our y equals 4.
Now we can put our y value in our chart, and we've got our first set of coordinates, whose values fit into our equation. If x equals 0, then y equals 4.
See, it's kind of like an if-then statement.
Now, in our same equation, let's substitute 0 for y and solve for x. This is just the reverse of what we did last time. So, 2x plus 3 times 0 equals 12. Well, 3 times 0 equals 0, so we've got 2x plus 0 equals 12. We then have 2x equals 12 and can divide each side by 2, giving us x equals 6. So, our second set of coordinates is x equals 6 and y equals 0. In our equation, if x equals 6, then y equals 0.
Now we have coordinates for 2 points, 0, 4, and 6, 0. The next step is to plot our points on a graph. So for the first point, we start at 0 on the x-axis. We don't move to the left or right because our x-coordinate is 0, so we just stay right here. Then, for the y-coordinate, we go up 4 places on the y-axis. So our first point is here. Now for the second point, we go over 6 for x and up 0 for y. So our point stays right here. Now we just connect our points to get the line. See how we only need 2 points to make a line?
Take the equation 3x minus 4y equals 12. Let's substitute 0 for x and solve for y. So, 3 times 0 minus 4y equals 12. Now, 3 times 0 equals 0, so we've got negative 4y equals 12. Next, we divide by negative 4 on both sides and get y equals negative 3. So, our first set of coordinates is 0 for x and negative 3 for y. Now, let's find another point. If we substitute 0 for y, we get 3x minus 4 times 0 equals 12. Well, 4 times 0 is 0, so we get 3x equals 12. Next, divide by 3, and we get an x value of 4. So, our second set of coordinates is 4 for x and 0 for y. Let's plot them.
Behold the graph. For our first set of coordinates, we're going to 0 on the x-axis. Then notice how we're going 3 places down on the y-axis. We go down because our y number is negative. We stick our point right here. Now to the second set. We've got a positive 4 on the x-axis, so over 4 we go. and our y value is 0, so we sit right here. Now we just got to put on our drawing caps to draw a straight line, and we've got it. We've successfully graphed the solution points of linear equation 3x minus 4y equals 12.
There are a couple of equation forms that will always get you the same kind of line. We're going to take a look at a few of them. Let's start with the recipe for horizontal lines. Remember, a horizontal line is a flat line that goes straight across. Let's see how it's written in the math community.
In equation form, it looks like this. Y equals c, where c is some constant number. This just means that we're going to have a particular value here. For example, 6. And this value is going to stay the same no matter what our x-coordinate is. Take a look.
So we've got y equals c, and the value of c is 6. We simply mark 6 on the y-axis and draw a horizontal line through it. Notice that when our horizontal line is drawn here, our y value will always be 6, but our x value changes. So we can have the coordinates 3 and 6, 4 and 6, 6 and 6, or even negative 3 and 6. Y stays the same, x changes.
What about a vertical line?
No problem. Remember that a vertical line is one that runs up and down. Plotting a vertical line is very similar to plotting a horizontal one. We just kind of flip the values.
The recipe for making a vertical line is x equals c, where c is some constant number. So if we've got something where c equals negative 2, then our x value always equals negative 2. This time, x will stay the same and our y value will change.
So, if we've got the equation x equals negative 2, then we just move to the left 2 spots on our x-axis and draw a vertical line. Note how the x values are always negative 2 and the y values change. For example, negative 2, 2, negative 2, 5, and negative 2, negative 4. Voila, your vertical line.
All right, it's review time. We started this section with the graphing basics. Remember that a graph is made of little square sections and is divided into 4 parts called quadrants. When we look for points on a graph, we're given coordinates which lead us along the x-axis and the y-axis to the point we're looking for.
Now we can also find points on a graph while we solve linear equations. We pick an x or y value and solve our equation to find the other. When we do solve the equation, we get our second coordinate and can plot a point on our graph. We can solve for as many points as we like, but we only need 2 points to determine a line. When we draw the line, it would be the graph of that particular linear equation.
Also remember the special equations for horizontal lines and vertical lines. For horizontal lines, we've got y equals c. Our y value is always the same, and our x value changes. With a vertical line, we've got x equals c. Our x value is always the same, and our y value changes.
How's about taking quiz 2?
Part 3, plotting 2 lines on the same graph.
Section A, 2 lines.
Sometimes you might be given 2 different equations and asked to find an x and y value that can fit into both of them and keep the equations balanced. One way to figure out which numbers will work is to plot the solution points for both equations on the same graph and draw the lines. The spot where the 2 lines cross will give us the coordinates that fit into both equations.
Let's say we have the 2 equations 3x plus 4y equals 12 and x plus 2y equals 0. We're going to solve them individually first, then put them on our graph and figure out where they cross.
For our first equation, 3x plus 4y equals 12, we want to plug in 0 for our x value and solve for y. When we do this, we get 3 times 0 equals 0 plus 4y equals 12, or 4y equals 12. We divide by 4 and get y equals 3. Our first pair of coordinates is 0, 3. Next, we substitute 0 for y and solve for x. Doing this, we get 3x plus 4 times 0 equals 12, which gives us 3x plus 0 equals 12, or simply 3x equals 12. We then divide each side by 3 and end up with x equals 4. So our second set of coordinates is 4, 0. Now we've got 2 points.
Now in this equation, we want to do the same thing. Plugging in 0 for x, we get 0 plus 2y equals 0, or 2y equals 0. Next, we divide each side by 2, giving us y equals 0. So in this equation, when x equals 0, y also equals 0, and vice versa. Notice if we put a 0 in for y, we'd also get 0 for x. That's the same point we just found. so we need to try another number to get a second point. Let's try 2 for x. Working this out gives us a y value of -1. So now we have our second set of points.
Our next step is to plot these points and draw the lines. So we plot our 4 points. Now we connect them to get our lines. Notice when we extend our lines, they cross at this point right here. This is called the point of intersection. The coordinates of this point, 12 and -6, will work in both of our equations. In our first equation, we plug in 12 for x and -6 for y, and see that it balances. And in our second equation, we plug in 12 for x and -6 for y, and see that it also balances. This means that we've done our work correctly, and this point is on both lines, and that's that.
Whew, that process was a bit lengthy, so let's do a quick recap of the steps we used. We started by getting solution points for both our equations. Then we plotted those points on our graph and connected the points to get the lines. Next, we extended the lines and found the point where they intersected. We then checked this point to make sure it satisfied both equations.
Okay, now that we know we can have 2 lines on a graph that intersect, there's something else you should know. It's also possible to have 2 lines on the same graph that never meet.
Kinda like if Bob was walking down Mill Avenue and Chester was walking down Spruce Street. The streets are right next to each other, but they never cross. So sadly, Bob and Chester never meet. In this situation, the roads are parallel to each other, and Bob and Chester are leading parallel lives.
The same thing can happen on a graph too. If 2 lines run next to each other and never meet or intersect, they're called parallel lines.
Now there's just one more thing to mark down in your little book entitled Everything You Need to Know About Drawing Lines on Graphs. There is the possibility that you can have 2 different looking algebraic equations which represent the same line. It's like if someone said, "Beautiful," and then expressed it in sign language. They are both different ways of saying the same thing. Well, with algebra, we can have one line on a graph that has 2 different equations to express it. Check this out.
We've got the 2 equations, -9y plus 6x equals 36, and 3y minus 2x equals -12. Well, if we kept working with these, we discover that they share more than one common point. The coordinates 0, -4, and 6, 0 work successfully in both equations. Because they share both of these points, this means they're both algebraic pictures of the same line. This is what happens when more than one set of coordinates works in both of our equations.
If we look closely at our 2 equations, we notice that the first is just -3 times the second, so it's really the same equation in disguise. Notice, if we multiply both sides of the equation by a number, in this case -3, it's still the same equation. We're just expressing it a little differently. This is what we mean when we say we have 2 different algebraic expressions of the same line.
All right, we've just polished off a whole nother section, so it's time to take a quick look back.
We started Part 8 by putting more than one linear equation on the same graph. By doing this and figuring out where the lines intersect, we get a set of coordinates that works in both equations. There are also lines that we can put on a graph that never meet, called parallel lines. And finally, if we solve 2 equations and find that they share more than one set of coordinates, this means they are different algebraic expressions of the same line.
Okay, now we're going to get into our time travel machine and head back to inequalities. Just like we did with equations, we're going to put inequalities on a graph.
Part 4, Graphing Linear Inequalities.
Remember a little while back we talked about inequalities, statements that had 2 unequal sides, like 9 is greater than 3. Well, now we're going to take those same sort of inequalities and put them onto graphs. So, let's get to it.
Section A, Drawing Inequalities.
Remember that an inequality is set apart by the fact that it has one of these 4 symbols in it: greater than, less than, greater than or equal to, or less than or equal to. It has these instead of an equal sign because the nature of the expression says that one side is not equal to the other. The way we put these lines on a graph depends on the sign in the inequality.
If we've got a plain greater than or less than sign in our inequality, then we're going to use a straight dotted line when we graph it. If we have a greater than or equal to or less than or equal to sign, then our line will be a solid one. This is just like using open or filled-in circles for inequalities on a number line.
So let's say we've got 2x minus y is greater than 6. For that matter, let's say we won the lottery and an all-expenses-paid trip to Hawaii. In the meantime, our ultimate goal is to draw a picture on a graph that will show where all of the correct solutions for our inequality will be. In order to do this, first we got to solve for some coordinates. We do this the same way we did with equations, by picking a value for x and solving for y. So let's take 2x minus y is greater than 6 and do the same.
The first thing we want to do is write our inequality down as if it were an equation. In actuality, it's still an inequality, and we're going to come back to it as an inequality, but writing it down as an equation will help us solve for points on the boundary line.
What's the boundary line, you ask? The boundary line is just the line we're going to end up with on our graph once we solve the correct points, plot, and connect them.
On one side of this boundary line, there'll be points that satisfy our inequality. On the other side of the boundary line are the points that don't satisfy our inequality.
Remember, satisfying our inequality means the points fit in our inequality so that it makes a true statement. Let's check out an example.
Say we've got 2x minus y is greater than 6. First we want to write it as an equation, so we change it to 2x minus y equals 6. Now, we proceed as usual, by subbing in 0 for x. Remember, we can choose any number for our x, but we're going to stay with the 0 because it's easiest. Subbing in 0, we get 2 times 0 equals 0, minus y equals 6, or just negative y equals 6. But we want a positive y. To get a positive y, we simply multiply negative 1 through both sides and get positive y equals negative 6.
Now we want to get our x value when y is 0. So we sub 0 for y and get 2x minus 0 equals 6, or 2x equals 6. We divide each side by 2 and get x equals 3.
Now we can plot these points, 0, negative 6, and 3, 0. Next we connect them with a dotted line. We use a dotted line because our original expression is an inequality, and we're trying to show something is greater than. If we had greater than or equal to, this would be a solid line. But it's just greater than, so we've got a dotted line. This is our boundary line.
Now on one side of our boundary line, there are points that will satisfy our inequality. Our task is to figure out which side has the winning points, and then shade it in. We can do this by choosing a test point. Any test point. We're going to use 0, 0 because it's usually the easiest. 0, 0 keeps the math simple.
So back with our original inequality, 2x minus y is greater than 6. We take the coordinates 0, 0 and plug them in, 0 for x and 0 for y. Doing this gives us a statement that reads, 2 times 0 minus 0 is greater than 6, or simply 0 is greater than 6. But notice this isn't true. 0 is not greater than 6.
Actually, it's no problem. Since the point 0, 0 did not satisfy our inequality and it's on the left side of our line, then we need to shade the opposite side, the right side of our line. This means all the coordinates we could ever choose on the right side of this line will work as solutions for our inequality. We show this by shading that area.
Now, if we want to double check to make sure we did this right, all we have to do is pick a point on the right side of the line and see if it satisfies our inequality.
Let's pick this point, 7, 0. When we put this into the inequality, we get 2 times 7 minus 0 is greater than 6, which becomes 2 times 7 is greater than 6, and 2 times 7 is 14, which is greater than 6. This means we were correct when we shaded the right side of the line. Our inequality is satisfied.
We're gonna do one more to get this shading thing down. Here we go!
If we have the inequality 4x minus y is less than or equal to 12, our first step is to write our inequality as an equation, then start substituting numbers in. Let's start by substituting 0 for x. When we do, we get 4 times 0 minus y equals 12. 4 times 0 is 0, so now we're working with negative y equals 12. Now we do our multiply by negative 1 trick and get positive y equals negative 12.
Now let's substitute 0 for y and solve for x. We get 4x minus 0 equals 12. We lose the 0, giving us 4x equals 12. Divide by 4 and get x equals 3.
Next, we plot the points and draw our line. Notice we've got a solid line this time around. Do you remember why we use a solid line? It's got nothing to do with mechanical pencils or the flimsibility factor of our wrists. It's because our inequality says that 4x minus y is less than or equal to 12. We've got that equal to phrase that tells us to draw a solid line. Now we just need to figure out where to shade.
If we choose the test point 0, 0 and plug it into our original inequality here, we get 4 times 0 minus 0 is less than or equal to 12, which equals 0 is less than or equal to 12, which is a true statement. So, because 0, 0 worked in our inequality, we're going to shade the side of our graph that houses 0, 0. Here the bottom and left sides are shaded, so any point in here will satisfy our inequality.
Okay, so when we graph inequalities, we shade the side of the graph that has the points which satisfy our inequality. Now let's get jiggy with it and do the same thing with two inequalities.
Section B, the intersection.
Okay, we've talked about points of intersection before, but this is just a little bit different. You know what that means. You gotta listen up.
Just like it's possible to have two lines on a graph, two equations represented on a graph, and two pieces of graph paper for breakfast,
it's also possible to shade more than one portion of a graph. This phenomenon occurs when we're asked to solve two or more linear inequalities and then graph their solution points on the same graph.
So it's really business as usual, except this time when we shade, we're going to have two shaded areas and we've got to figure out where they overlap. Let's say we have y is less than 6 and y is greater than or equal to 2x minus 3.
We've got y is less than 6 and y is greater than or equal to 2x minus 3. Remember, we write them as equations first, getting y equals 6 and y equals 2x minus 3. Now, let's pick some coordinates for these guys.
Notice how we don't have any 0 coordinates this time. That's just to show how the whole process still works without them. For instance, in our second equation, if we choose a value of 4 for x, we'd get y equals 2 times 4 minus 3, or 8 minus 3, which gives us a y value of 5. That means we've got 4, 5 as a set of coordinates. And when it's all said and done and dinner's on the table and the cats come home, these are the lists of coordinates we get for each equation.
Plotting the points for our first inequality, we've got 2 and 6, 3 and 6, and 4 and 6. And for our second, we've got 2 and 1, 3 and 3, and 4 and 5. When we connect our points, our lines look like this. These are the boundary lines for our two inequalities.
Now we're going to figure out where to shade our graph. Remember, we do this by choosing a test point and plugging it back into our original inequalities. We're going to be using our old faithful 0, 0.
For the first inequality, y is less than 6, our dotted line. Notice we only have a y variable here. There's no x, but it's no biggie. We just plug in 0 for y and get 0 is less than 6. Since this statement is true, we shade everything below the line, because our test point, 0, 0, is below the line and it satisfies our inequality.
For the inequality y is greater than or equal to 2x minus 3, we plug in 0 for x and y and get that 0 is greater than or equal to 2 times 0 minus 3. Simplified, we've got 0 is greater than or equal to negative 3. This is a true statement. Now we shade to the left side of the line because 0, 0 satisfies this inequality, and 0, 0 falls to the left of the line.
Check out this spot on our graph where the two colors overlap. This area is called the intersection. What's cool is that any set of points you pick from anywhere in the intersection will satisfy both of our inequalities.
Let's test this with coordinates 2, 3.
Plugging in the coordinates in the first inequality, we get 3 is less than 6. Remember, we just plug in the y value here because we don't have an x. This checks out because 3 is less than 6 is a true statement. With the second inequality, we plug in 2 for x and 3 for y, and get 3 is greater than or equal to 2 times 2 minus 3, which equals 3, is greater than or equal to 4 minus 3. Finally, 3 is greater than or equal to 1. This is also a true statement. Since the coordinates we chose from the intersection satisfy both inequalities, we know we shaded the correct portions of the graph.
All right. We're bordering on the edge of this tape, so let's take a quick review of the stuff we just did. When graphing inequalities, we start by treating them like equations so we can plug in numbers and get coordinates for the boundary lines. We then plot our points and draw our boundary lines. We want to test our inequality by choosing a test point and seeing if it satisfies our original inequality. We usually use 0, 0 to test because it's easiest, but we can really choose any test point. If our test point satisfies our inequality, then we shade the side of our line that houses the test point. If it doesn't satisfy our inequality, then we shade the opposite side of the line.
We can also have two inequalities represented on a graph. If there is an area of overlap, or an intersection, then any coordinates of a point in this area should satisfy both inequalities.
Quiz 3.
Phew! Now we've really come to the edge. That's all that's fit to print for Pre-Algebra Part 2. Remember what we've been through over the last hour and a half. Linear equations, the golden X, graphing, absolute value equations, linear inequalities, and so much more.
We hope the pumped-up world of pre-algebra helps you get where you need to go.
If you have any questions, make sure you give us a call here at 1-800-238-9669. We'd love to hear from you.
And be sure to check the store for other standard deviance titles like
The Really Big World of Astronomy, The Adventurous World of College Algebra,
There it is.
The Deep Fried World
Of Organic
Chemistry,
and the anatomically correct world of
Anatomy.
And there's so much more than that.
Much more.
Bye-bye.
Thanks